Hey there, welcome to another edition of Mr. Weis Solves an Old AP Problem. Today we're going really far back to 2007, number 5. An interesting problem involving a spherical balloon. So here's the issue. The volume of a spherical hot air balloon, so very big, one of these big balloons, expands as the air inside the balloon is heated. The radius of the balloon in feet is modeled by a twice differentiable function r of time, where t is measured in minutes and the radius is measured in feet. So we know that we've got this function r, which tells us the radius of the balloon in feet at any time t in minutes. We are told from 0 to 12 the graph of r is concave down from time 0 to 12 minutes, and we are told that the second derivative exists. It's twice differentiable. And here we're given a table of values for selected values of the derivative of r. So every one of these values is measured in feet per minute. So at time 0, the radius is increasing by 5.7 feet per minute. And it looks like as time goes on, the rate of increase is decreasing. So it's increasing very fast at first. The first couple of minutes it's increasing very fast, but by the 12th minute, we're not gaining many feet per minute. And thinking about these sort of things can be very helpful for a problem like this. We're also told that the radius of the balloon is 30 feet when t equals 5. So r of 5 is 30. Okay, so the first question asks us to estimate the radius of the balloon when t equals 5.4. So our goal is to estimate r of 5.4. Now, how do we do that? It says using the tangent line approximation at t equals 5. Okay, so we want estimate, part A, estimate r of 5.4 using the tangent line at t equals 5. Okay, so no big deal. The equation of a tangent line, this is straight up Calc AB, right from the beginning stuff. What's the whole point of the derivative is to help us get the equation of the tangent line. So the equation of the tangent line is y minus r of 5, which is 30, equals r prime of 5, which is 2.0, times t minus 5. So again, this is just r of 5 that's going here, and this is r prime of 5 that's going here. And this is the equation of the tangent line. What we're going to do is we're going to plug in the time 5.4 into this and see what we can get. So we estimate now that r of 5.4 is approximately equal to 2.0 times 5.4 minus 5 plus 30. Let's see, so that equals 2 times 0.4 plus 30, which equals, let's see, so that's 30.8. And we want to make sure that we don't forget units. This would be in feet. 30.8 feet. Now there is a follow-up question, which is this an overestimate of the actual value or an underestimate of the actual value? I believe that's the way it's worded. It says, is your estimate greater than or less than the actual value, and give your reason. So let's think about this. One of the things we're told is that r is in fact concave down. So we know that r kind of looks like this, concave down. Let's see, actually, we don't know that it looks like that. It's concave down, but it's increasing, because we can see that r prime is positive all the time. So it's concave down, but increasing, so it kind of looks like this. And what we did is, like, here is at t equals 5. We found the tangent line at t equals 5, and here's 5.4. We plugged that into the tangent line instead of the actual value of the function, so we can see that it is an overestimate. So this is likely greater than r of 5.4. And the reasoning I would give is, since r is concave down, I probably would include a picture, perhaps a little better than this one, but I probably would include a picture as well. Okay, here we are doing part B of the 2007 number 5 AP Calculus BC exam, in which we're dealing with this hot air balloon that's the air inside the balloon is being heated up, which is causing the radius of the hot air balloon to increase over time. We're given a lot of information about this, including, but not including the actual function that defines the radius at any moment in time. Instead, we have some values of r prime. What part B is asking us to do is to figure out what the rate of change of the volume is. Rate of change of the volume of the balloon when t equals 5. So, in other words, what they want us to compute is dv dt when t equals 5. This is our goal. It's a straightforward related rates problem, and what we need to do is come up with some way of relating the variable that we want to know something about to the variable that we do know something about. When I say variable, I really mean function, because these variables are actually functions of time. So we need something that relates volume to radius. But this is a straightforward, you should all know this, although they actually give it to you on the AP, so you didn't even need to know it. Volume equals 4/3 pi r cubed. I'm going to implicitly differentiate both sides of this equation with respect to time. So the derivative of v with respect to time, I don't know what it is. We call it dv dt. On the right-hand side, I'm going to have to use the power rule on r. 4/3 pi's are just constants. So the 3 is going to come down, leaving me with a 4 pi, leave the inside alone squared, times the derivative of the inside, according to the chain rule. The derivative of the inside, or the inside is just r, and the derivative of the inside, we don't know what that is, but that's just dr dt. And now I'm ready to plug in and focus on the moment of time in which we're interested in. So dv dt equals 4 pi, and then I'm plugging in r of 5 squared times r prime of 5. This ends up being 4 pi times 30 squared times r prime of 5 is 2 times 2. So that's 900. 30 squared is 900 times 8, so that's 7,200 pi. Now we want to make sure we use the appropriate units. They actually ask us what the appropriate units are. So this is a rate of change of volume, so it's going to be a rate. It's going to be something per time. In this case, time is measured in minutes. The thing that it is the rate of is the volume, though, and volume is like a length cubed. The length we're dealing with here is feet, so this is feet cubed, or cubic feet per minute. And that is my final answer. Okay, here we are for part C of this problem involving a growing balloon, a hot air balloon, in which we're told we're interested in a function which tells us the radius of the balloon at various times, but we are only given specific values of this. So part C asks us to do something kind of interesting. They want us to estimate the definite integral of r prime of t from 0 to 12 using the chart that we have here. What we're going to do is Riemann, a finite Riemann sum. We want to use 5 rectangles, and we're using the right endpoint, I believe. Let me just check that that is the case. 5 subintervals, and the right Riemann sum. Okay, so this is pretty straightforward. We're adding up a bunch of rectangles. They gave us exactly the right amount of numbers. So I think the first rectangle is the rectangle where we're going from time equals 0 to time equals 2. So the width of that first interval is 2 minus 0. And the height of that interval, since we're using the right endpoint, is going to be r prime of 2, which is 4.0. 4.0. So just to be clear, this is the width, which is 2 minus 0. And this is the height, which is r prime of 2. If you multiply the width times the height of a rectangle, you get the area, and that's our first rectangle. In the second rectangle, the width this time is 3. That's because the width is 5 minus 2. And the height this time is 2.0. That's because this is r prime of the right endpoint, which would be 5. Plus, so we're using, let's be clear here, these are unequal intervals, okay? Usually when we do Riemann sums, we often we assume that all the intervals are equally spaced, but we don't have to. We can make estimates without this. The next interval goes from 7 to 5, which has a width of 2, 7 minus 5, and a height of 1.2. This is r prime of 7. We're up to 3 integrals, 3 rectangles, 2 more to go. Plus, now we're going from 11 to 7. 11 minus 7 is 4. 11 minus 7, and the height this time is 0.6. 1 more to go. This time we're doing 12 to 11, a width of 1. 12 minus 11, and the height this time is 0.05. Sorry, 0.5. I should have said this is r of 11, and this one is r prime of 11. These are all primes of 12. All right, cool. So let's see. Get out the calculator and add up these values. Hopefully I don't mess this up. I brought a calculator with me. So let's see. I might be able to do some of these without. So I've got 8 plus 6 plus 2 times 1.2 plus 4 times 0.6 plus 0.5. That is, in fact, 5 numbers I added up there. 1, 2, 3, 4, 5. And I end up getting 19.3. Now we should try to figure out what this is. In fact, it asks us to explain what this is and make sure we use the right units. So ultimately, so let me back up actually. I shouldn't have an equal sign here. I should have an approximate sign because that's what this is approximately equal to. What this integral actually equals by the fundamental theorem of calculus part 1, what this thing actually equals is the antiderivative of r prime, otherwise known as r, at 12 minus r of 0. So you should note that this is the difference between two r values, which are radii in feet. And so this is measured in feet then, definitely. And what this represents is the change in the radius from times 12 to times 0. This is the change in radius from time equals 0 to t equals 12. And so that would be my answer to this. Okay, here we are on the final part of this problem, 2007 number 5, where we're dealing with this balloon, hot air balloon that's being filled with air, or the air is heating up, which is causing the balloon to increase its volume and its radius. We have this function r that's keeping track of the radius. In part C, we had computed or estimated this indefinite integral, the area under r prime from 0 to 12, using right Riemann sums. And in part D, they're asking us, is this an over or underestimate of the true value of this definite integral? So I think some pictures and just a sentence here is really all you need. You were told that r is concave down. What that means is that r double prime is negative. What that means is that the derivative of r prime is negative. So here's what you know. R double prime is less than 0. So what that really means is that the derivative of r prime is less than 0, which means that r prime is decreasing. Now I do not know if r prime is concave up or concave down, but I do know that it's decreasing. So what I know about the graph of r prime is that it looks something like this. R prime either looks something like this, or it looks something like this. In either event, it's decreasing, or it could be a mixture of these. It's just got to be decreasing. But the point is, we used right rectangles to estimate this sum. So when I use right rectangles like this to find this, to estimate this area, whether it looks like the first thing or the second thing, it doesn't matter. Both of these are underestimates. So this must be an underestimate. And that's my final answer.